We talked about nitrogen. Then we talked about carbon. Then we now talked about transition elements. Okay, yeah, that's true. Atomenu by industrial chemistry. Right? Then we looked at metals. Then under these metals, we talked about sodium, talked about calcium, aluminum, talked about tin, that's SN. Talked about lead. Did we talk about lead? No. Copper, then iron, right? Okay. Then I think we talked about the rate of chemical reaction, right? Rate of chemical reaction. Then we also talked about acid, base, and salts. Okay, water and pollution, have you? Okay, now listen, hey, understand that frequency. Now, this, if you understand the meaning of this class, all your attention will be focused on the board and the sound you are hearing right now. At this moment, yeah, thank you. At this moment, yeah, at this moment, if you understand the value of this class, believe me, you won't even see the person sitting down beside you. And all you see is the board, and all you'll be hearing right now is the sound. Because at this moment is what you are using to test your ability, what you have learned so far. And we are using this to revise, like a preparation. So this is the point for you to know, okay, under all this influence of these topics, am I ready? So when you understand these concepts, now, like I say, what you're going to face right now is a law of determinants in your future, right? So which means do not, listen, do not see the person beside you. All you have to hear is the voice here. Now, we started this class by looking at separating techniques. I'll try my best to touch questions in each of these topics. I'll try all my best to touch questions, and I'll try to see if I don't finish them today, by next week as well, the class will still be revision, continuation. Now, we are done with, that's the normal class we're doing. So still be revision and question. Now we start with the first one, and that's what we call what? Separating techniques. Hey, Omaba, I'm telling you something. This is not a time to greet your friend, though. Stay in that frequency. Now, when you look at your UTME question, you understand that most of the time, the first and second question would always come from what? Separating techniques. Separating techniques. It's like a normal stuff. Oh, yeah. Now, understand at this level, I want to believe that you already have the concept, but what we are trying to do now is to build your level. See, one thing that makes you outstanding in UTME, especially when it comes to chemistry, is your ability to make that critical analysis and make that final decision of ticking your answer. Listen, for those of you that have done mock, you will understand something that as you were reading the questions, there were some answers you were picking with 100% guarantee to more. And that's because the moment you start reading the question, you understood the principle behind that question. Got that answer, yellow me. See, this is not a question where you read and you don't know. Chemistry is when you read the question. The moment you understand the principle that governs that question, then you'll be able to pick your answer with 100% assurance. That means the reasoning is there. Now, there were some questions that you were half baked. You know what I'm talking about for those of you that have done mock, which means those questions you were able to select two that you know can't be correct. Then you are now confused or you are stranded between two options where two of them appear to look what? Correct. Hey, answer ọmọdé yóò sin frequency. Listen, if at this moment, if I see your eyes closed, you are standing, no, there's no. Some people, there's nothing we can do about their matter. Just like these two fell. Now go. The principle matters a lot. So when you're under this void, understand that we are trying to take you to that atmosphere where you can read questions and you can make a very good conclusion. A very good conclusion. Now, we start by saying separating techniques. Now, the first question you ask yourself, why do we carry out separating techniques? Hey, listen, I'll be going at a low, steady, fast pace. It is a low, steady, at a fast, at go back. When you go follow frequency. Now, why do we carry out separating what? Technique? Hey, listen to what I said. Do not see the person beside you. Mario, that girl, stand. Stand. Sharply, sharply, sharply. Don't, when I say stand, seconds, 34, okay. Hey, stand. Why do we carry out marker for many marker? Okay. That song cannot live. Now listen. Why do we carry out separating what? Techniques. Oh yeah. The major reason for carrying out separating techniques is to have what? Obtain useful and important. Okay. But what's the main reason? Thank you. That's the word. The major reason for carrying out separating techniques is to obtain what? Pure substance. Listen. The major reason we carry out what? Separating techniques is to what? Extraction of metal. Is it a form of separating techniques? Why? We want to remove the what? Impurity and get a what? A pure what? Metal. Hey, listen to what I'm saying. So the main reason for separating techniques is to get what? Pure substance. Now, how do we now know if a substance is pure? Okay. Now we want to do separating techniques to obtain what? Pure substance. Then now, how do we know? That was a question in UTM on its own. How do you test for purity? The aim of separating techniques is to get what? Pure substance. Now, how do we now know if a substance is pure? Actually waited. Are you getting? That is what? Boiling point and what? Melting point. Now, please note it down somewhere. Boiling point and melting point is used. So these are focused on what we have seen in your past questions. So boiling point and melting point is used to what? To determine purity or test for what? Purity. I'm going to answer. The boiling point and the melting point. Then other things you can use is what? When the substance is colored, you can use what? Chromatography. How many spots will you give on chromatography? 1 spot. So when a substance shows 1 spot on what? Chromatography paper, then that's what? Pure substance. Now listen, I'll be looking at some of the core concepts. We're looking at some of the core principles that are being used in separating techniques. Now, what's the difference between a mixture and a compound? You know, a compound can be represented by what? The major reason for separating techniques is to what? Obtain a what? Pure substance. Now, we are growing together in that chemistry. Follow pace. The major reason for separating techniques is to obtain what? Pure substance. Then, how do we know if a substance is pure? Melting points, boiling points, chromatography, density. Now, look at where UTM can be very interesting. You get to example. Chiamaka opens the first question. Next. And here, which of the following can be used to test what? Purity? The moment you see that question, you are happy. right? Because you know the principle. Then you now see option A, wrong. Option B, boiling point. Your brain triggers. No, there's when you see the right answer and it just trigger like, okay, this is it. Then while you are being triggered, you just go down and now see melting point again. Yes. Have you seen that question you tell me? Where they put boiling point and what? Melting point. And your teacher has said in the class, boiling point and melting point can be used to determine what? Purity. And here you are in the exam hall seeing what? Boiling point and what? Melting points. Kaidaba. Oh yeah. Then we are trapped, Abby, in between melting and boiling points. Now the question now is, which of them will now be the most appropriate to what? To determine what? Purity. It depends on what? But this question does not put the state of matter. It is boiling point to be for what? Liquid. Then it is melting point to be for what? Solid. Fine. But when you now have a question that does not indicate the state of matter, then what do you pick as that? Is it what? Where do you pick melting point? Mongo. Now listen, that's what, see, we are that frequency. These are possible things you can't come across. See, these are stuffs you might likely face. That's why I said the realm is what? To move you to that aspect where you can read questions. Listen, there are some questions that are very easy to answer. The drying agent for ammonia. Could need stress. If they say CaO, they see more. Who are painful? That the drying agent. What's the process for producing? What's producing contact process? Okay, let us take this UTM question. Contact process is used to produce dash. Then you now see SO3 and you see H2SO4. What would you produce? You see SO3, Alaja, SO3 and H2SO4. We are not here to confuse you. We are here to perfect your understanding. You see H2SO4 and you see SO3. And they say contact process is used to produce what? What's the equation for contact process? SO2 plus what? O2. What's the catalyst? Vanadium 5 oxide. To give what? SO3. This is contact process, right? So it is used to produce SO3 or H2SO4. Okay, because it was SO3, they will have stopped at what? S. Make, but those are the analyses you should be able to make. Or else, hey, see, I used to tell you the most painful thing is being average in chemistry. If you don't understand, the most painful thing is being what? Average. When you are trapped in between two options, hey, very painful. That's one well. Hey. I don't say you are not sleeping. Now, but we now go back now. We now say, what can be separated? Remember now, always remember that when we have matter, I'll be giving just like 2 questions on this, then we'll just move. Matter can be classified into pure, right? And what? Oh, maybe one free question. The pure and what? Impure. Now, under the pure, what do we have there? Element and compound. Then under the impure, what do we have here? Mixtures. Now, we note something. Under separating techniques, what are we separating? Are we separating element or compound? Okay, Moronkola Malik. Moronkola Malik. What's it called? Mr. Adams is calling you. Moronkola. That's H2SO4. Okay, Maxwell Moses. I think your mom is waiting for you downstairs. Maxwell Moses. Don't call the last. Maxwell Moses. Okay, so we'll come back here. Sorry. So what can be separated is what? Sit down. What can be separated is what? Mixture. Now, why can mixtures be separated? They are physically combined. We'll take that particular main reason. Because they are not chemically combined. Yes. Heterogeneous because that's the key thing there. Mixtures can be separated because what? They retain their what? Properties, their individual what? Properties. So when I have a mixture of sugar and water, the sugar is still what? Sugar, and the water is still what? Water. Hey, I want you to go to answer. The sugar is still what? And the water is still what? So we can now separate them based on the fact that they still what? Retain their what? Properties. So mixtures can be, are you noting these things? Mixtures can be separated because they retain their what? Properties. So we separate them based on their what? Properties. Don't got answer. Now, if you have a mixture of two liquids, there are two things that will happen. Is that they mix or they don't mix, right? So is that they are mixable or what? Immixable. Is that they are what? Now, once you have a mixture of two liquids that are not mixable, what do you use to separate it? Separating funnel. Are you getting the concept? So the moment they are mixable, what do you use to separate them? Distillation or what? Fractional distillation. Hey, are you getting principles? So when I have a mixture of two liquids, if they do not mix, e.g. kerosene and water, what do we use? Separating funnel. But when they mix, e.g. ethanol and water, we use what? Distillation or what? Fractional distillation. Now, when do you use fractional distillation? When they have what? Close boiling points. If the substance can sublime, what do you use? Sublimation. And that's example one. Example one. How can a mixture of ammonium chloride, 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 ammonium chloride, comma, sand, ammonium chloride, comma, sand, and water be separated? We have a mixture of what? Ammonium chloride. I must stay in that frequency. We are not doing optional. We are solving. Ammonium chloride, sand, and what? Let's say water. It's what I want to say. Ammonium chloride, sand, and what? Salt. Now, hey, that guy is stretching. Obi, the moment you want to separate this component, we have the ammonium chloride, we have the sand, we have the what? Salt. See, Iwoluma low analysis. By looking at the components we have there. Now, in this component, what do we have? Ammonium chloride, sand, and we have what? Salt. Now, what is unique about ammonium chloride? It can what? Sublime. What is? You can't see from that side. Okay. When you say ammonium chloride now, we said, what is unique about ammonium chloride? Sublime. What is unique about, what can we talk about this sand and water? If we add water, salt what? Then sand will remain undissolved. So it will be abnormal to have a mixture of salt and sand, and you want to unpick. I get now. So it's not even achievable. So the first thing, so which means for us to separate it. Now, this is the question. We know that we need the solution to separate the what? Salt, to make the salt dissolve in water. Now, the question now is, are we going to start with sublimation before dissolution? We start with what? Sublimation, then what? Dissolution. Then after dissolution, filtration. After filtration, evaporation to dryness. Elijah, why can't we use crystallization? Or when do we use crystallization? Number one. Cannot retain. Cannot withstand. I want to get any shot. Okay, so you get the concept. So which means crystallization, hey, okay, go on, Timon. So Crystallization and what? Distillation can be used to separate two mixable liquid, Abi. That's solvent and solute, Abi. But the difference is that distillation is used, sorry, evaporation to dryness is used when the salt is what? Stable to what? Heat. That is when the heat cannot affect the composition of the what? Salt. So what was the concluded arrangement for separating this now? We have sublimation. After sublimation, then we have what? Dissolution, Abi. Then after dissolution, we have what? Filtration. Then we now have what? Evaporation to dryness. Then we use crystallization. Yeah. Salt are not stable to it, like copper sulfate. Copper sulfate comes out with crystallization. So which will be the purest? Crystallization and evaporation to dryness. So you can know that crystallization produces pure what? Solute more than evaporation to dryness. And now you tell me question. The purest way to obtain sugar is via what? Crystallization. So I'll take one of these questions. It says, which of the following techniques okay, now someone said the difference between fractional distillation and destructive distillation. Now, fractional distillation is used to what? To separate mixtures, right? Then destructive distillation is the breaking down of what? Of one of the amorphous of what? Carbon. So the breaking down of carbon is what we call destructive what? Distillation. But fractional distillation is used to what? Separate mixtures of two liquid that are what? Mixable and have close what? Boiling points. Yes, I have a question, Lee. I'll take one more question on separating techniques. Then we can proceed. If a material can be magnetized and another material cannot be magnetized, how do you separate them? Magnetism. Now look at this. Which of the following technique will be used in food industry? Which of the following will be used in what? Food industry. We have distillation, chromatography, filtration, fractional distillation. The answer is what? In food industry. Food. The most appropriate will be what? Chromatography. Because it has to do with color. Color. How then? Then, assuming they have even specified, but since they said just food industry, then the best standard what? The chromatograph. Because food has to do more of a deal. Because most of the food, have you heard about this food coloring? Yeah. Then in the case of production of ethanol, what did they use to separate? Production of ethanol. Fractional distillation. That's distillation. When you have, yeah, because ethanol has a boiling point of what? 78. And water is what? 100. Okay, let us take one more question. Sulfur is soluble. Is it a polar solvent or non-polar solvent? So what are the solvents for sulfur? Benzene. That's a question. One more question. A mixture of iodine and sulfur. Oh wait, see, when it comes to separating techniques, that's what you have in there. The major purpose for separating techniques is to have a pure substance. How do you know if a substance is pure? Melting or what? Boiling points. What's here? Then when there's impurity, what happens to boiling points? The melting point is what? What do you call that property? That property of increasing and decreasing of melting points. About engineering, so answer. That property is known as what? Colligative property. Hey, colligative. Atisoteleo. Colligative properties. So one of the applications is pouring salt on ice, Abi, to make the ice what? Melt what? Fast. Like I said, your attention here, please. Now, a mixture of iodine and sulfur, a mixture of iodine and sulfur, a mixture of iodine and sulfur, a mixture of iodine and sulfur can be separated by dissolving in A mixture of iodine and sulfur can be separated by dissolving in option A, you have benzene. Option B, you have what's it called? Trichloromethane. Trichloromethane. Then option C, you have water. Then option D, you have ethanol. So we have a mixture of what? Iodine and what? Ethanol. And the question is saying, how can we separate it? So iodine and what? Sulfur. How can we separate it? A mixture of what? Iodine and what? Sulfur. And we are now giving what? These options. What's peculiar about trichloromethane? It is used for what? Anesthesia. It is also used for what? Yeah, preserving dead bodies as well. But you know they have stopped it, right? Because it's affecting what? The liver. So apart from this, which other compound can be used as anesthesia for minor surgical operation? N2O, laughing gas. Hey, stay in that frequency. We don't care. All we are saying, these are possible stuffs. Now, we have a mixture of iodine and what? Sulfur. A mixture of what? The process used for the production of sulfur, what do you call it? We call it what? Flash process. How many pipes is dig inside? 3. Stay in that frequency. If the person beside you is answering questions and you don't know it, ask the person. Make sure. There's no joke. So if I ask a question, the person beside you know the answer and you don't know it, ask the person. I'm alpha. If he doesn't answer you, fight here, full blow. Is that now? Now we have what mixture do we have there? Iodine and what? Sulfur. Now, you know, when we have sand and water, what did we do here? We dissolve in what? Water. Why did we use water? Because salt can dissolve in what? Water. So that makes us to separate the water. Now, we now have iodine and what? Sulfur. Now, which of them will dissolve in any of this now? Who will dissolve in benzene? Sulfur. So when sulfur dissolves in benzene, what will be left? Then they can do what? Hey. Listen, if in the option we have sublimation, which of these can be used to separate? No, iodine can sublime, right? But solid iodine, right? But in this case, we are just giving that what? Sulfur and what? Iodine. And we are giving a solvent. So the question is to look at which of them can dissolve in the solvent. And that's what? Who will dissolve in benzene? Sulfur. So that means sulfur will dissolve in what? Benzene. Then after is that dissolve, what do we do? When sand and water, we dissolve in water, then what do we do next? Filtration. So when I have this now, when we dissolve it in water, what's the next we do? Filtration. What's here? What? What other solvent do we have for sulfur? Carbon disulfide. Actually, carbon what? What about toluene? Yeah, toluene is also an example of non-polar solvent, just like benzene. See, the likes of all those toluene are derivatives of what? Benzene. That's separating technique. So, to that the question, go. Iodine can also dissolve in what? Ethanol. There's possible iodine, but the one that is possible there is what? The benzene. What's here for the sulfur? Now, so I take this question. This last question that will now move. This question is based on chromatography. You know, chromatography is used to dissolve what? To separate what? Colored mixture. If you know how important chromatography is, is iodine polar? Yeah, the iodine atom, right, is non-polar. Okay, because when you have non-polarism, when you have unequal sharing of electron. So when you have iodine and iodine, they both have the same strength. So the compound will be neutral. So some of you don't know the importance of all these things we are talking about. But let me give you one application so that you know how important it is. I was reading an article one day that says that if you write to the president of USA, probably it's like you just threaten that guy or you just write any letter, and the letter gets to the office of that guy. Once they see that writing, that letter, they will trace the maker of that biro. They'll do what? They'll trace the maker. They'll know where the pen, that ink, that country, where that ink came. How are they able to do that? By the process of what? Separating techniques and what? Analytical what? Chemistry. They can analyze it. So all these things we are saying, by the time you guys get into that and they open chromatography for you, Kaida, hey, over, she chromatography for you understand that it's another word of his own. But what we are saying is that understand the basic principle here. Now, in chromatography, we have a stationary phase, have we? What's the stationary phase? The paper. Ah, God bless you. The stationary phase is the what? Paper. Now, what's the mobile phase? It could be ethanol. It could be another thing. So what do we call it? The solvent. Now, the separation of chromatography is based on what principle? The migration. Hey, that guy, God knows all here. So chromatography separates based on what? Migration of the substance in the what? Mobile what? Phase. Do you understand that? Sublimation is used to separate a substance that can what? Sublime from a substance that cannot what? Sublime. Alaja, stay in that frequency. Now, that's talking about the case of what? Separating techniques. Now, when we now come to atomic structure, we know that all matter is anything that has what? Stay in that frequency. Anything that has what? Then one, me, anything that has what? Mass and occupy what? Space. What do we call that? Matter. So this aspect has little calculation, but it is more of analysis. One more. Hey, one more day. Now, this aspect, that was when we started about the origin of. In fact, this is where we have the aspect of chemistry being expanded. And most of these things happened in the 19th century. Although there are some guys that talked about it earlier on. Oh, yeah. Yeah, we can consider that as well. But I just picked that option just to explain for benzene. What is called? Sulfur. But mostly in that solvent, you might not see like ethanol there. Because iodine can dissolve in what? Ethanol. Yes, I believe it for instance. We say matters are composed of what? All living things are made of solid or what? Gas. My go to enclose out there. Now those are three. Now, but the concept was this: what people were now bothered. What are the things that are made up of matter? What is present inside matter? Who was the first guy to talk about this stuff? If you're in that class, that's who? Democritus. Hey, I'm gonna go on to answer. What did the guy say? What did that guy say? What to Pepsi? Eh? All matters are made up of what? Atomos. That was the word he used. He said all atoms, all matter rather, are made up of what? Atomos. A small particle, right? Now, who came to challenge that guy? Those guys that back. You know, who came to challenge him? Aristotle. Sorry on your mind. Now, what did Aristotle say? He said all matter are made up of what? 4 elements, Abi. That's the avatar, Abi. Now, who came to antagonize that concept? John Dalton. He now said all matters are made up of what? Small particle. He called them what? Indivisible part, which he called what? Atom. Hey, don't go down so. All matters are made up of what? Atom. Now you understand some of the concepts we are talking about here. The concepts that we are talking about here. Now, when he said all matters are made up of what? Atom. He made some theory, Abi. What do we call that theory? John Dalton what? Atomic what? Theorem. But this is, see, this is, I think someone was telling me is having difficulty getting the names of these scientists and their contribution. Oh, simple. But maybe sometimes I don't know. But let's take some of their names. We have atom, right? What are the 3 fundamental particles? That was one UTME question one year, I think 2006 or so. And they asked them, what are the fundamental what? Particles. What are the fundamental particles? We have that what? Proton, neutron, and what? Electron. Now let us look at contributions. Before we now go into solving questions. Discover proton. So which means Brother Rutherford discover what? Proton. And how did he describe an atom? You know, he discovered proton, right? Then what did he use to describe an atom? Plum pudding was J.J. Thomson. That's the name of the experiment. How did he describe an atom? He said an atom has what? A central positive small what? Nucleus. And what's surrounding it? Electrons. And that made us to have what? So he talked about the planetary structure. So whenever you are drawing this structure, where you have 2, 8, I mean, when you are drawing this thing, remember that it was my friend that what? Gave this design. And that's who? Rutherford. Planetary structure. I'm still going to explain something about this now. Now, we now have the like of J.J. Thomson, right? What did J.J. Thomson achieve? He achieved what? Electron. And what? Charge to what? Mass ratio. John T. Olong, don't miss up all this. Your syllabus specified that students should know the name of scientists and their contribution. Their names and what? Contribution. Now, it was J.J. Thomson that tried to describe nucleus as what? An atom as what? The plum what? He described it as plum pudding. Right? That's PU, right? That's the model. Was this model accepted? So what he just described is now as what? The plum pudding. PLUM PUDDING. I'm going to clean that very fast now. Now, after that guy, no, we have already proton, we have electron, Abi. So proton is who? Proton is who? Planetary structure is who? J.J. Thomson. Then charge mass as well. Kill answer. Oh, yes, I got. Now, it means one fundamental particle, Abi. That's neutron. Then who discovered neutron? That's what James Chadwick. John C. Olong. This name, this could be one mark that can separate you from 300. Oh, yeah. My fault. Then, for us to now get the charge of electron, charge of what? Electron. That's what? Robert what? Millikan, right? What did he do? Oil drop experiments. And these are names. Now, Chuari, don't always confuse this Neil Bohr and Rutherford. Hey, let me give you the difference. Let me give you the difference. Because I was in that room that day when, Nigbo, I'm serious. That very day. Listen to what happened. When Rutherford was in the room and they asked him, Alpha, come and explain to us what do you think an atom look like? He came out. He had this British accent and a little of ghetto language too. More serious. He speaks broken too. So go and check. Rutherford broken language. Now, when he came outside, he now said, atom, hey, I'm telling you exactly the way he said it. I was there. He said, atom has a small place in the middle. Do you get now? He called that place. He said that place is positive charged. Are you getting now? And it carries majority of the mass. I was like, okay, because I was behind him, telling him to ride on. Now listen. He now said, surrounding the atom, that small place, the nucleus now, surrounding it is where we have electron. This electron has surrounded what? The nucleus. Then someone now asked him, someone stood up from the crowd and was like, if electrons were moving around the nucleus, they were supposed to radiate energy. I think that guy came from Oxford. I can't remember his name. No challenge without that. If these electrons were moving around the nucleus, it was supposed to what? Radiate what? Energy. And when they radiate energy, they were meant to disappear inside the nucleus. Oh, yeah. Rutherford said, well, he spoke to you about that day. Nigbo. Now listen, he said, well, taking it. So I don't understand what they said. But what he knew was that electrons were moving round. Oh, yeah. Then Nebo now signaled to me that how far should I proceed? Because all of them respect me a lot. She understand. Hey, listen. Now, when Nebo now signaled me like Alpha, shaking proceed, and I said, Nebo Alpha, one of them come on. So Nebo now stood up in that same crowd and I said, this guy is correct. Then I like, okay, Baba, come and prove it. He now came outside. He said, the electrons are moving around the nucleus, but they are not just moving around at a random space, that they occupy a particular position. They now looked at me. I said, call that place orbit. Now I said, Washiri. So stop making me feel like I'm lying. I get now. He said they occupy what? A particular what position. Now, you know, said that position, when they are in that position, they are moving around, they don't radiate what? Energy. Then I say, okay, so which means that position is what they call what? Orbit. Okay. Rutherford just said their planetary structure. It did not explain further. So it was Nelbert that now came to see that these electrons are located in what? A particular position. And that place is what? Orbit. He now said the orbits, I told him to wait, but later I shall say it should continue. That these orbits have different what? Energy level. So the lowest is what? K. Because my friend name was Kabiru then. That's why I started. I get it. We have a friend. So we use the name of our friend. That's K. Don't worry, I'm not, because if you look at I'm lying, you will not believe. L was in respect of Lavoisier. Yeah, so you have the KLM. That was how Nelbor was able to explain or discover what we call what? Orbits. What's another name for orbits? Shell. These are names of the scientists. But what was the limitation of Nelbor? Nelbor could only explain for what? Hydrogen. After, hey, Alaja, I will bite you now. I'm telling you a story that far back. Tell me. So, Nelbor could not explain beyond what? Hydrogen. Not worry. When you gain admission to schools, you start fighting with the rest. I best might expand. Now, so that is how, these are the names of the scientists. Now, but get something, get some informations. An atom, is an atom positive or negative? An atom is what? Stop giving me wrong answer that will be making me. An atom is electrically what? Neutral. And what's the reason? The number of proton is equal to the number of what? Electron. Hey. The number of what? Proton is equal to the number of what? Electron. I get what I say. So we are looking at this. Now, understand something. Note this for your A-level and advanced classes. Although we say atom has 3 fundamental particles, are these the only 3 things present in an atom? No. Apart from these 3, they see other 70 particles. Yes, up to about 70 particles present inside the atom. But we call these 3 the what? Fundamental what? Particles. But yeah, they are the one primarily responsible. But that's what I'm talking about positron, quarks, or to yakmaloben. Do you get what I'm saying? Now, what are the possible things that can be tested here? Can I clean this side? So the names, their contribution, all of are gone. Now, after this now, we're able to look at what we call isotopes, right? What do you mean of isotopes? So isotope is when an atom of the same element have what? The same atomic what? But different what? Sorry. The same atomic number, but different what? Mass number. The same atomic number, but different what? Mass number. In this aspect, UTM will not ask you to calculate. Sorry, to define, Abi. But majorly you can do what? Calculation. Now, in 30 seconds, let us get this answer. An atom of lithium, an atom of lithium, how are you guys coping? That's nice. An atom of what? Lithium has 2 isotopes, Li. Okay, did I say lithium? Lithium is element number 3, Abi. So you have Li73, 90%, and Li63, 10%. 20 more seconds. If the person beside you is doing it and you don't know it, you have 90% Li73 and 10% Li. The answer is what? 6.4. Without solving, God said, oh, you're going to go show 90% 7, and 6% 3. 10 more seconds. The answer is what? But the answer is 6.9. And so sometimes when you pick options, you know you are correct. Your answer must be closest to the one that what highest percentage. What's here? Highest what percentage. Now let's take this last question under that same isotopes before we proceed. 2 isotopes of chlorine. 2 isotopes of chlorine. 2 isotopes of chlorine. Who was that guy that discovered isotope? Frederick Soddy. Oh yeah. And Frederick Soddy. Who are no now? Mafo. Frederick Soddy. That's how I call him. He was one that discovered isotopy. But that's not part of your Jamb syllabus anyway. The next question, what do you say? 2 isotopes of chlorine. 2 isotopes of chlorine exist in 1:3. Exist in 1:3, comma, Cl 3517 and Cl 3717 respectively. 2 isotopes of chlorine exist in 3:1. Then you have Cl, sorry, it's 3:1, please. 3:1, 3517 and 3717. 3517 and what? 3717. Calculate the relative atomic mass. What's the answer? To calculate the relative. If you carry calculator for this exam, the answer is what? 35.5. 35.5. Now, still under the atomic structure. So what's the formula we use for calculating? For some that like to use formula, what's the formula you use? R1 M1 plus what? R2 M2 divided by what? R1 plus what? R2. You know this equation is continuous, right? Yes. Yes, I believe. They not give what? That's the 3:1. No? So if you, yeah, if you can like, okay, listen, let me just solve down. In case they give you in this value, not in percentage, what is the mass of the first one? What's the abundance? 3. That would be 3 times what? 35 plus, what's the other one? 1 times 37, I mean, divided by 3 plus 1. So sometimes they give you percentage. So when you multiply, what do you have? Everything. But what will everything shall give you? That's 35.5. So sometimes they can give you in percentage, sometimes they can give you what? Ratio. So that ratio still means what? The abundance. That's how you I told you I'll be slow. Oh yeah. Go by 1. Now, we are still in the atomic structure now. If you have an element X, we have A, Abby. Sorry, A is Z is here. Then we have A here. Hey, listen, over. This, what do we call this A? Sorrow. Atomic what? Mass. Leave the fan. The sound going safe. If we have A and we have Z, this A is known as what? Line sorrow. Atomic what? Mass. What makes up the atomic mass? Proton plus neutron. Proton and neutron collectively, what do you call them? Nucleon. Then this one, what makes up the atomic mass? Proton only. I mean, so A represents what? Atomic mass. Z represents what? That's the atomic what? Number. Now, which of them is responsible for chemical properties? That's what? Which of them is responsible for chemical properties? Listen, which of them is responsible for chemical properties? Now, when we say chemical properties, say when sodium is exposed to the atmosphere, stay with me. When sodium is exposed to the atmosphere, what happens? Hey, Omoyogbo, sit up, sit up. So when you expose sodium to the atmosphere, right, it will react with what? Oxygen to form what? Sodium oxide. The sodium oxide will do what? React with water to form what? Anyway, now, but what determines that sodium is very reactive? Is it the atomic mass or the atomic number? Atomic number. What's the name of that science that I told you died in the is it First World War? Yeah. And what? Mostly. At what years? At what age? Let us leave that story. It used to pain me. Odisonu. What we are saying is the guy that discovered that atomic number is responsible for chemical properties. His name is what? Henry Moseley. That discovered that atomic number is responsible for what? Chemical properties. That was the guy I told you died in what? Second what? World War. In the year 1914. And we told him not to go. Konigbo. Yes, now. I was in that room together. I've not been lazy. I've just been safety conscious. Oh, yes, but now this is where I'm going. Hey, but an atom is electrically what? Neutral. Yeah, write this question. What is the number of proton and electron? What is the number of proton and electron? Stretch. It's okay. It's allowed. What is the number of what? Proton and neutron. Proton and electron. Okay. That's what you guys wrote at me. Yeah. What is the number of proton and electron present in? You write the structure. Al 27 13 3 plus. Al 27 13, then you have 3 plus. What are we looking for? Number of what? The number of proton and what? Electron. Now, in this compound, we have 27 13 Al 3 plus, Abi. What does this 3 plus indicate? It has what? Lost 3 electron. Hey, Kemi. Electron, where do you find them? Where do you find them? Orbits. Electrons. What is the name of the force that hold the electron close to the nucleus? Hey, Kaida, how does we? You are there. Yes, I got. Now, this 3 plus, go of time factor. Now, this 3 plus indicate that what? This atom has lost how many electrons? 3. Now, hey, understand that you cannot lose proton. No. Why? The proton is where? Inside the what? Nucleus. What is the amount of energy required to separate the nucleus? The force holding them together. Hey, binding energy. The amount of energy required to separate what? Proton and what? Nucleus. The strong what? Nuclear force. The amount of energy that is what? Holding them together. Go now, so which means in this atom now, how many protons do we have? 13. How many electrons? Why is it 10? That's lost because normally the number of protons must be equal to what? Number of electrons. Yes, I take these 2 follow-up questions. What's the number of proton, electron, and neutron? Question mode. Let me tell you something. If you can pick all these small questions, don't see. Some people have learned so far that when they ask them number of proton, what if rate of chemical reaction, organic? Sometimes they just ask you simple questions. Don't go and read and forget simple ones. So just open question. Count it. What's the number of proton? Like Indomie. Take it up. What's the question? What's the number of what? Proton, electron, and what? Neutron. What's the number of proton, electron, and what? Neutron present in 1? Uranium 236 92. Number 2, O16 8 2 minus. The number of proton, electron and neutron present in uranium 23692 1682 minus. Who was his name? What was that scientist that discovered radioactivity? And what? Becquerel. What did he observe? What did he observe? Hey, so what did he observe? Uranium salt. And what did he observe? A photographic plate became what? Darker. Hey, Amaka Fumini Maka. I'm our studio for here. Amaka Fumini Maka. What's the answer for the first one? Yeah, electron is what? 92. Proton. Neutron. What? 4. Yeah, number of proton. Electron. Neutron. What's here? Those are some simple concepts to my back body under the know the name of the scientists, know the fundamental particles, know how to count proton and electron, understand when they are positive, lost electron, and when they are negative, they have what? Gain electron. Good answer here. Which one is that? This one. This one. Yeah, that's number of proton. And number of proton is equal to number of electron. How many electron is equivalent to one proton in terms of mass? That's approximately the 1,840 electron is equal to what? One proton. When the mass of the mass of 1,805 is actually 835. Summarize that 840 is equivalent to what? The mass of one proton. So we go to back 1,840 electrons together. That's now equivalent to what? One proton. So proton is the one that carries the what? The mass. Why electrons are the one that carry the what? Charge. Then one more thing before I go. Before we go to the next topic. What is that principle known as the uncertainty principle? Heisenberg principle, Abi. What did that guy say? You cannot get what? Momentum and the position simultaneously. You can't get the momentum and the what? Position. Ma for we go to 98. Yes, now 100 Abi. What possible now for? So now we are just thinking now look at it now. Hey, that girl respect. You know that it was Neil Bohr that stood to defend Rutherford Abi by saying that what? Electron occupy a special place where they don't radiate energy, and he called that place what? Orbit. Okay, now when that guy discovered that orbit, that now triggered the likes of me. But here, and other scientists, we're now trying to look at how is this electron arranged? Hey, how are they what? Arranged. Now, last right now, that's one that leads us what we call electronic what? Configuration. Surely, I swear, if you understand that electronic configuration, it will help your understanding of bonding. So yeah, because bonding there are 3 types of bonding majorly, right? Ionic, which is what? Metal and what? Non-metal. So once you see a metal and a non-metal, they have what? Ionic bond. Then when you have non-metal and what? Non-metal, they have what? Covalent bond. Engineering, I'm not hearing their voice there. So when metals and non-metals, what do you call those ones? Metallic bond. Metal and metal rather. You call them what? Metallic bond. Don't care. Well, I'm here beside you. Don't switch off. See, we have not gotten to the point where we start using principles. All these ones are the normal ones, normal statements. But them I get it. Oh yeah. Now, one of the concepts is this now. Now, what is of we have shell. Kemi. Cholele. Ugba flat. Self-contained. One way Latin con. We are torn like that. Uh-huh. I said, once you understand electronic configuration, oh God. See, when we are doing this topic, remember I told you guys that periodic table is known as the what? Map of chemistry. So that see, once you understand periodic table very well, it's like you have known your way. There's things in there. What's that group that has metal, non-metals, and metalloid? They have metal, non-metals, and metalloid. Group 4, Abi. Until I swallow someone in this class, you will not stop. No, seriously, not play. I'm party me. Some of them have jack overnight. I've never been here before. One day by linear. Are there? Hey, are you following the frequency at all here? So we now say the arrangement of the electron, right? We give you a map of that chemistry. So once you understand, well, because of you, I came here. So the moment you know the arrangement, you are able to analyze it. And one of the ways to understand the arrangement is to understand what electronic configuration. And what's the major thing in electronic configuration? See, when we started this chemistry, I told someone, I said, chemistry is like a language. It's not even like a language, it's a language. That's what we do here. Everything we are saying is not about the word, it's about the interpretation that comes after you hear the word. When I say electrolyte, forget the word. What is your brain thinking about the electrolytes? Mine, I just sit and I came to and I said, nga, 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 nga. Your brain just look like Kinwi, Kinso. You get now? But when you hear some sound like stand up, your brain can interpret that stand up. Then you now look at it. Is this person at that position to tell me to stand up or not? I mean, now, if it's not in that position, what do? You extend the slap. That's what happens. So when sodium sees copper, when sodium sees copper, sodium like I didn't say that too. So which means understanding chemistry is like the language. Now, understand I said the periodic table is like the map of what? Chemistry. It's the map of chemistry. Now, let's now look at how do we understand the periodic table? One of the ways to understand the periodic table, hey, one of the ways to understand covalent bond is to look at electronic configuration. Now, let's get this right now. What is electronic configuration? This is what? Arrangement of electron into the what? Orbits or what? Orbitals. Hey. Arrangement of electron into the what? So again, into the what? Orbits or what? Orbitals. See, will be this aspect. Sorry, oh, brother. Kemi, Ronke, leave the fan. Arrangement of electron into the what? Orbits or what? Orbitals. Now, am I arrangement? I don't want to claim this side because that's the old guideline. I don't understand. Why is time running like that? I'm seeing after 11. Kilo day. Time sorry. Now, let's take a look at this now. Under that electronic configuration. Now, we have this part that Neil Bohr gave to us, a central plate. What? Nucleus, Abi. So that's what's in nucleus. What was that scientist that discovered nucleus? Rutherford. Then Neil Bohr now told us that, no, Rutherford said it's planetary. But when the last one, okay, this one has the first what? Orbits. Then we have another one, which is what? Then we have the what? And all these orbits are based on different what? Energy level. Oh yeah. Now we have the first shell, the second, and the third. We got them on so yeah. Now we now look at see. Let me tell you something. The electron that enter each of these orbits is not given by a particular formula. What's that formula? 2n squared. So which means this particular orbit can take a maximum of what? 2 electrons. And that's brother Kabiru. I won't tell you the other names because you guys, when I say Kabiru, believe me. Then this next one can take a maximum of what? 8 electrons. Then this bros here can take how many? 18. Don't say it too. The maximum number of electrons that can enter here is what? 8. Now this is known as what? The K element, I mean. What's the maximum number of electrons that can be found in a shell? The maximum number of electrons that can be found in a shell, final answer is what? Engineering is how many? No, bro. I'm engineering got down. The answer is what? 30. What about the G orbitals? How many? 15. Although we can have 15 in that G orbital, but mostly the maximum number of electrons can have in the shell is what? 32. Now, this is for K element, Abi. Now, but when we are filling orbitals, when we are filling what? Orbitals, we are looking at what? S, P, D, F. The S, these are the suborbitals. These are the subshell. Abi? These ones here are known as the subshell. This is known as the what? Orbit. Or this is not the orbit, or you call them what? Shell. The subshell are the what? S, P, D, F. Now, inside this subshell is where you know how they call the what? The orbitals. S has how many orbitals? How many orbitals? Engineering, how many orbitals? How many orbitals here? Yeah, exactly. Don't get it mixed up. 1 orbitals and can take what? 2 electrons. Mama, I'm engineering. 1 orbitals and what? 2 electrons. Electron is likely to be found in a shell, orbit, nucleus, or what? Atom. So the place where you have the highest probability of finding an orbit, an electron will be in the what? Shell or orbit. That's the option. Because shell is another word for what? Orbit. So they call it electron cloud density. Now, Jack Basibai. So this is shell. This is what? Subshell. So this one has how many orbitals? 1. P has how many orbitals? 3, Abi. Then D has how many orbitals? 5. Then this bros has how many? 7. Oh yeah. Now, inside each orbital, what's the maximum number of electrons? 2. That's the answer. Now, we fill this subshell using which principle? You know, there are 3 principles there. Half-bar principle, Pauline exclusive principle. Let me son. Hey, Obi. Hey. If that is you close again, we'll fight. It's you I'm talking to. But there are 3 principles there. The first one is what? The half-bar, Abi. Half-bar, what does it mean? The building of electron, filling of electron from the what? Lowest energy level to the what? Lowest energy level to the next high what? Energy level. That guy in black, don't leave me. Yes. Stay with me. Now, we have the half-bar principle. We have a rule that calls what? The Ohm's rule. Then we have the what? Pauline exclusive principle. What's here? Now, I should ask a question. We are just revising. Then we now move. What's the shape of S orbital? That could be your question, no? What's I need to say menu. I'm not saying that could be the question. The shape of what? S orbital. And they may not ask anything on predictive again. That's why I used to tell students, pray and be prepared. So here, pray and be what? Prepare. See, do you know that you can get to that example and everything we just be the one that said the question? Oh yeah, it will just be like that. That's praying and being prepared, reading like so that the question looks, they are just familiar. What's the shape of p orbital? Dumbbell. You know, p and f, we don't talk about their shape. Why? Both d and f is what? Complex. And different materials give different names. There's actually no uniform name. So most times your question does not pass S and what? P orbital. S is what? Spherical. P is what? Dumbbell. Now, try the méjì key element SPDF. Which of them is more detailed? SPDF. There are three informations we can get here. Sorry. You can get to know if an element. You can get to know if an element is a metal, non-metal. You can get to know the group and the period here. I mean, the position, the periodic table, I mean, check on the verse on here. But this one can give you more information. If you are using this, you cannot know if the element is transition or what's it called? Inner transition. What's here? Now let's now take a look at this now. If I have okay, alpha principle, we have talked about this, Abi. What does the Ohm's rule talk about? Electron must be what? Singly filled before what? Pairing. Now for easy stuff, let us do alpha principle. Is in your note there how you have the arrangements. Let us take for example by the electric configuration of sodium. Sodium is Na11, right? And this guy called Henry Moseley made us to understand that we should focus on atomic number. My gear Jensen. Now, if I'm using key element, okay, this is what? 281. If I'm using alpha principle, that's what? 1s2, 2s2, 2p6, 3s1. Now let me just tell you this. Some students prefer this bros here. Yeah, this one is very fast. Sometimes if you are giving this information and you're good at this, it's good to just add up the whole number. If you are very fast to this. But if you are very okay, but there are some questions that there's no way you can, there is no padasibi. You have to use this. Write this question. What's the number of unpaired electron? What is the number of unpaired electron? What is the number of unpaired electron present in chlorine atom? What is the number of unpaired electrons? Stay with me. Hey, wà pẹ̀lú mi ọmọdé. Kàyí dàbà. Stay with me. What is the number of unpaired electrons present in chlorine atom? That's the first question. Hence, indicate if the atom is paramagnetic or dimagnetic. Those are questions that you can only get using the words alpha what principle. Okay, take us share together. They will now come back to some experts here. No, we are using chlorine, Abi. Now to get for chlorine, what do we have? 1s2, 2s2, 2p6, Abi. 3p what? 5. Hey, okay. Look up. This is how you answer this kind of question. This is how you answer this kind of question. One of the things to do is do not focus on these ones here. Because all of them must have. The one we focus on is what? Which is 3p what? 5. So Lord, P has how many orbitals? I can't hear your voice. How many? How many orbitals? 3. So we're going to have 3p5, I mean. It has how many orbitals? 3 orbitals. That's 1, 2, 3. What's here? Now, we want to fill how many electrons here? 5. But there's a guy called Ohm's rule. If I tell you why we call this guy Ohm's rule, you don't understand. He's a very good friend of mine. It's because he's very that's why we now call him Ohm's. What's here? He's a very good friend of mine. Now, the guy said, you first fill in what? You first fill in the orbitals, and that's in what direction will they face? Clockwise. That's all pipe. So you have what? 1, 2, 3. Out of how many? 5. How many is remaining? 2. So we're now filling the other what? Anti-clockwise, Abby. 1, 2. And what are we looking for? How many what? Unpaired. And how many do you have there? 1. Now, in this question, will this atom be paramagnetic or diamagnetic? Paramagnetic. Why? Because it has what? Unpaired electron. Question down question here. Now, what does Pauli exclusive principle talks about? Yeah, that's for the normal magnet. Yeah. Are we there? We are there. So what does the Pauli state that? Electron was what? No. The Pauline exclusive principle are what? Yeah, no two atoms can have what? The same 4 quantum what? Numbers. Yes, I call it. No two atoms. That's the Pauline exclusive what? Principle. No two atoms can have the same 4 quantum numbers. No two atoms can have what? Same 4 quantum what? Numbers. So alpha principle, the building up principle. Okay, let me come back to this. Remember, what's electronic configuration? Filling of what? Electron into the what? Orbit or what? Orbitals. How many subshell do we have? 4. SPDF. Now, they can say right. Now we said sodium, Abi. Sodium. Sodium is 281, Abi. Then if you are using the alpha principle, what they have 1s2, 2s2, 2p6, 3s. Now, look at this now. It is not of importance to just know how to write this. The most important is the information you can get from this. Ọmọdé ìgbọ́n nǹkan tí mo sọ. Kókò ọmọ 281 does not even make you an outstanding science student. What makes you outstanding is what? The information you can get from that 281. Now, how many shell is here? 3 shell. Abi? What are the shell? K, L, M. So automatically, what period does it belong to? That's period what? 3. Which means elements in the same period have the same number of what? Shell. Then this one belongs to what? Group what? Group 1. Metal or non-metal? Metal. So any element that has between 1 to 3 is known as what? Metal. The number of electrons in the outermost shell, what do you call it? Valence electron. Now, if you look at this information here, what group does it belong to? That's group what? 1. What about period? Period what? 3. What block elements? S block. Those are the things you cannot get from this aspect here. This is what? X block what? Element. If it stops on P, you call it what? P block. So what D, you call it what? D block. Now let's take a look at now. That's for the electronic configuration, Abi. Who was the name of the guy that designed the periodic table? What? Mendeleev. What? Mendeleev. He arranged elements in order of what? Atomic what? Mass. He first did that, Abi. Then you know that when was the guy? Mendeleev, when he designed the periodic table, no noble gas has been discovered then. What's here? As at that time, there was no noble gas. And remember in that class, we talked about why his table was given recognition. What was the reason? He could what? He could predict the properties of elements that have not been what? Discovered. Example of one element he predicted, which is now what? He didn't call it gallium. Gallium is an element now. Eka aluminium. Eka aluminium. Then later it was now, I think, Eka G or something. Then later it was now what this, because it was able to. Now, who now came to bring the new periodic law that edited it from atomic mass to atomic number? Who is that person? Henry Moseley, see that guy? Henry Moseley, he was one that predicted that no, these things are determined by what? Atomic number, not what? Atomic what? Mass. Now, there are two properties of periodic table, which is what? Group and what? Period. This is another opportunity to explain properties that change. Yes. Yes. This time, to get and bang, all she is doing these keys. This is another opportunity to know it again. So I'm going to do for the representative elements. So we are in that periodic table now. No, we have hydrogen, Abi. Then we have helium. Then we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Then we now have sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium. No, scandium, all those ones will be somewhere in between, Yabi. But you can look first 20. Now, okay. These are the first 20. What do you call these first 20 elements? Where do they fall? What kind of elements? Representative elements. Representative elements. Now, okay. Please, don't you alone call mocking insane. You know that these bros here, in some textbook, they'll just put it here. In some textbook, they don't include this guy. He's an outcast. Half-cast. Mogbo. He doesn't have what? Now, which means hydrogen can actually fit both in group 1 and group 7. So for convenience, some will just put it here. But for this class, they'll just put the guy here. Because I can hear him telling me, put me in group 1, put me in group 1. No need to be chemistry, they are my bone elements. No, now you are not getting it. They will speak to you. Yes, now you just be sleeping, you see chlorine. It will just come and say, I am chlorine, I am greenish yellow, I am called chloro because of this. And you just have the, mouth. That's like Berlin. Now, what we are saying is this. This side here is the left hand side, I mean. And this is what? I'm about to go around. See, I'm telling you, don't see anybody. Don't hear anything. Anything I'm about is my voice. Now, the left side, on this left side, what is present here? Metals. On this side is what? Non-metals. On this side is what? Metals. On this side is what? Non-metals. So which means as you are going like this, hey, that guy. As you are going like this from metal, what happens to metallic property? So it's okay. So metallic property is what? Decreasing. Now that process of changing, does it happen sharp? No. These ones are very reactive metals. Group 1. Hey, we are trying to analyze something to you. These metals, what are they? Very reactive metals. So as you are coming here like this, what happened? It will what? Reduce. By the time you get here, you will now start to meet what? Non-metals. You can see metals. As you are moving from metals, you meet what? These semi-metals. And if you go and check the complete periodic table, it's like a ladder that separates the metals and the non-metals. It's not a sharp line. So you have boron is a non-metal, to silicon, to gallium, and that's how it continues like that, like a ladder. Now, the moment you are now coming, what happens to non-metallic property? It starts to what? Increase. Here is the metallic property, and here is what? Non-metals. Hey, on the left side is the what? Metals. It's the only exception there. So on this side is what? Metals. So as we are moving down to this side, it turns to what? Semi-what? Metals. From semi-metals to what? Non-metals. See, that's how you interpret what's called your periodic table. Now, if you're now coming down, what happened to the metals? Are they more reactive or less reactive? More reactive. So which means, brother, potassium is more reactive than what? Sodium. Sodium is more reactive than what? But when you come here, it's quite the what? Opposite. As you are coming down, what happened to non-metallic property? It what? decreases. So the most reactive metal, will it be up or down? Down. The most reactive non-metal, will it be up or down? So from this table, what's going to be the most reactive non-metal? Did I hear helium? The answer will be what? Why didn't we call this group the noble gas? Or what do I personally call them? Boy group. Yes. I call the group 8 the what? Big boys group. That's are looking for election. Yeah, they want to donate. The guy is just chilling. Why? Because every other element want to be like the what? The big boys. Trying to join them. So we call them the what? The inert, noble, or what? So anything in reaction does not consign them. I get what I'm saying. It does not consign them. Struggling. Looking for this one, no? They just sit down, they chill. But remember, there's always that person that will always behave abnormal. So there's always a member of this group too that we see go. I don't know what he's looking for. What's that element? There's a member of this group, xenon. Actually, xenon is a member of this group that still undergo what? Reaction. Xenon is, yeah, some part of xenon. Almost all elements have a radioactive isotope. You get now. Now, like I was saying now, you are going down the group. What normally happens now? Metallic property what will increase. Now, all those ones are general understanding you need to know. But what are the things that will test your understanding on? Number one, let us start with the atomic size, which is almost same like the atomic radius. If you are coming down the group like this, what will happen to the size? Let us use this group here. Lithium is what? 2,1, Abi. Sodium is what? 2,8,1. Potassium is what? 2,8,8,1. What's here? 2,8,8,1. So which means you can see why they are increasing. Why are they increasing? Because of an increase in the number of shell. So we know that down the group, atomic size what? Increases. Very good. We are getting to another part now. Now, lithium and beryllium, which one is bigger? They have the same number of what? Shell. So for that reason, there should be what? The same thing. My boss even say explain this thing to you. Yes. Yes, I go. Lithium and beryllium, who will be bigger? Lithium is what? Bigger. Okay, now let's say it now. Wait you. Fluorine and lithium, who will be bigger? No, bro. Okay, when we look at atomic size, we focus on what? Lithium. Because your answers are making me want to dance. Don't be confused, though. Hey. Oh, yeah, but listen. We are getting to that part I think by next 2-3 class, we should do revision of everything. We are getting to that part where noise 2-3. I think we have like 3 classes left before your exam now. Like 2 classes, are we? I can't share vision because before some of you go and embarrass me in exam. Pastor, say Bokni. Go on, so very important. Hey, that atomic size, what are very important? When I ask you lithium, some of you are focused on atomic size. It's big. Now, okay, there's one thing that determines atomic size, and that's the force of attraction between the nucleus and the outermost electron. Now, let me just explain this. Like Laurier, man, see, at this point, don't see anybody. Let us say you look at lithium. What's the atomic number of lithium? 3. Beryllium is how many? 4. Carbon, how many? Boron, Abi? Boron is 5. Carbon is what? 6. Hey, okay, I'm going to use a simple model. In the nucleus of this bros here. Oh, Kogbo. Stay with me. In the nucleus of this bros here, we have how many proton? So it's okay, how many proton? 3 proton. Moving around it, is how many electrons? Ah. The number of proton is equal to the number of electrons. 3 proton, 3 electron. We come see after this explanation. Personally, I'll be passing through your mind to know if you have understand. Yes, you just wait. You see, you just hold on. You see a flash. I'm the one that is checking something. This one has how many proton? 4. Surrounding this proton is how many electron? This bros here has how many proton? Surrounding is how many electron? This one has how many proton? Proton, right? Then surrounding it is how many electron? Now, remember that 2 of them have the same number of shell. That one is constant, I mean. Listen to this, though. Very important. Now, how many electron is equivalent to 1 proton? 1,840 electron is equivalent to what? 1 proton. So which means proton has enough mass. Now, hey, if you need to listen, now, how many proton is electron here? 3 proton is what? Pulling how many electron? You are going to make the judgment yourself. 3 proton pulling how many electron? 3 electron. When we step further, this one, how many proton is pulling? How many is pulling here? How many is pulling here? 6 proton and 3 proton. Which of them will pull the most? Which of them will pull the most? So which means 6 proton, we have more force to pull the 6. Remember, electron is fele. Mélòó lára electron? Because we need how many electrons to become 1 proton? So what is now 6? What is now 6 electron to 6 proton? So the fact that we have 6 proton pulling how many electron? 6. The force of attraction is what? More. So this bros here, we put the electron closer than the what? 3 proton. So what will happen to the size of this one? It will be small because the force pulling it is what? Much. So as you are moving from left to right, atomic size what? Decrease. Why? The force of attraction is what? Increasing. So here, so don't forget when part of matter control save. Oh, Afa is you. Okay, what we just said is this. In the nucleus here, how many protons do we have? 3. Surrounding this proton is how many electrons? 3. That's at the ground state. So this one, as you are moving, the number of protons is increasing. So we are now saying that 3 proton is pulling 3 electrons here. By the time you move here, 4 proton is pulling how many electrons? 4 electrons. By the time you get here, 5 proton is pulling what? 5 electrons. So because of the force of attraction, so out of this whole line now, which of them will have the greatest force of attraction? 6, because of that's 6 proton. So this 6 proton will pull more electron closer than 3 proton. And when you pull it closer, making the size of the atom to be what? Small. So which means if you are moving from left to right, the atomic size will what? Decrease. There was one UTME question. In fact, UTME is crazy sometimes. They know that you know. See, there are 2 sets of students. One did not even know what's happening there. Oh yeah, that's one. Another set, see, some students have read this thing. All they know is that atomic size decrease, increase down the group, increase across the period, electronegativity increases from the left, decrease. Sorry to the core. Now, when you want to catch that student, is that thing you know they'll not put there? Atomic size decreases from left to right. What in Because the one you have come, they have right here there. Then I say because. Why not? Okay, so that's what you have to understand. That the sign now, what we are saying is that atomic size decreases from what? Left to right. And what was the reason? Because of the increase in the force of attraction between the nucleus and what? Outermost what? Electron. More time, sorry, continue. How would they hear me now? That's talking about the atomic size. So whatever atomic size or affect atomic size, we also what? Affect atomic what? Radius. Yes. Yeah, that's the nuclear charge or the force of attraction. Yeah, the nuclear force of attraction. I know. Is that not nuclear force? Intermolecular forces. Van der force, that's bonding now. Yeah, that's like a weak what's it called? Intermolecular force. A weak intermolecular force. Oh, yes, Agbalin. Now, apart from IE, then another thing we have is, no what? There's something we call IE, Abby. That's the last one we're talking about because of time factor. IE is what? And that is the amount of energy that is what? Required to remove one electron from an atom at the what? Gaseous state. Yes, I go. Down the group like this. Down the group like this. What happened to IE? It what? It decreases. Then across the period, it what? Why does it decrease down the group? See, there are two things. Yeah. Yeah. Okay, the first one we explain now, this one here, that's the nuclear charge. Then that screen effect is what we are now looking at in terms of ionization energy. Now, let me look at this now. Man. Look at sodium and lithium. No, sodium is 2,1, Abby. Then what is this one? This is sodium, Abby. No, this is 2,1. This is 2,881. You get now? Now, when you not talk about the screening effects, now that is talking about when you look at this out electron, maybe we have a force holding it, Abby. And remember that this force, what do metals do? Metals donate what? Electron. Now, when you look at this lithium and you look at sodium, which of them do you think will donate electron easily? Sodium. Why will sodium donate easily? The electron is what? Farther. Now, the fact that the electron is farther, that's due to what? The screening effect. So all this electron in between will reduce the force of attraction between this last electron and the nucleus. So that's what we call the screening. The screening effect is what? When the inner electrons reduces what? The force of attraction between the electron, that's the valency electron, and the what? Nucleus. That's the screening what? Effect. The screening effect is when the inner electrons, that's the core electrons. The screening effect is when the inner electrons, or you call them the core electron, reduces the force of attraction between the nucleus and the valence electron. They reduce the force of attraction between the nucleus and the what? Valence what? Electron. So this makes lithium, or what you call sodium, to donate electron better than what? Lithium. Thank you very much for your time. We'll continue from there in next class.